Welcome to circle geometry. We get started with sort of an introduction lesson today and go through some terminology that's important for the rest of this unit. Keep this page handy, you might need it if you have to refer back to some of the things we talked about kind of later on in the course. All right, we're going to start very simply right now with the circle. And I think that the first thing that anyone would say about a circle is that it's round. That's a good definition maybe when you're in kindergarten. But moving forward in grade 9 and through high school, we're going to talk about circles in respect to their centers. You'll see center labeled O. That's common. You'll hear that a lot. It doesn't have to be O. It's just arbitrarily named so. But the definition of a center, of a circle, excuse me, is all the points that are equidistant from that center point of the circle. So all these points on the outside edge of the circle are exactly the same distance away from the center of the circle. And so this ray of points, and when they're all joined together, there's infinite amount there. All those points, that's what creates a circle. So the words you might have heard there is equidistant. So equidistant meaning the same distance. Okay. All right, some special parts on the circle. I'm sure you're familiar with these ones already, but that distance, that equal distance that we have in the circle, that's called the radius. The radius is the measure from the center of the circle to the outside edge of the circle. Okay, and so like I said before, all the radii in a circle are going to be the exact same length, because the distance from the edge to the center of the circle is exactly the same. Okay, so radius for one, radii for plural. And you'll see that shorthand, of course, with the letter R. Jumping kind of to the top right-hand side here, we're going to talk about diameter. So a diameter is actually a chord that touches both edges of the circle, but it has to pass through the center of the circle. So you see it goes through center O here, and the diameter is the distance from one edge to the other, but it has to go through center. Okay, so that's the key to the diameter. The diameter does another thing. It actually creates the semicircle. So the semicircle is the half circle. I'll switch colors here. So here in red, we see the semicircle, and of course there's another semicircle in the other half. So we have the diameter, which is a chord going through center, and that cuts the circle into two equal parts. That creates the semicircle. You just heard me use the word chord. Here it is right here, chord, C-H-O-R-D. So a chord itself is just any line that has endpoints on the edge of the circle. So you see we have an endpoint here, and a line going straight through here, touching the edge of the circle. That's a chord. Chords can go anywhere. So we can have a chord from here to here. We can have a chord going from here to here. All of those are chords. A diameter is also a chord, but remember the diameter is a special chord. It's going through the center of the circle. All right. Some words that aren't on here, but I'm just going to add. We can just add them maybe to this diagram or color. The distance around a circle. Okay, so when we measure the distance around a square, we call that the perimeter. But for a circle, it's actually called the circumference. Okay, and I know you know that. Circumference is something we learned earlier in grades 7 and 8. There's a formula for circumference of a circle, and there's two different ones. We can say circumference equals pi times d, or we say circumference equals 2 pi r. And that should make sense because remember the diameter is going to be the same thing as 2 radii. Okay, so the diameter is 2 radii. So we have two formulas for the circumference, pi times d and 2 pi r. Pi, remember, it's just that 3.14, blah, 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 goes on forever. Never-ending number that was discovered in terms of the measurements of circles. That's where pi comes from. All right, moving on. These terms we're going to see quite a bit this year, so it's important to understand them. The first one is called the perpendicular bisector. I kind of think it's almost like a superhero name. I'm the perpendicular bisector. It's is exactly what it says it is. Okay, it involves perpendicular lines. So remember, perpendicular lines meet each other, make a 90-degree angle, and it bisects. Bisects, that's cut in half. Okay, so over here on the diagram, we see that we have a perpendicular set of lines. They're meeting each other, making a 90-degree angle. And this line coming from center down and intersecting this chord cuts this chord equally into two pieces. That's the bisect part. So if we had from here to here, that would be the same as from the center out to the edge again. So that's the perpendicular bisector. Perpendicular line that cuts something in half. Pretty easy. All right, two different types of angles we're going to go through. Central angle, again, the title gives it away. Central angle has its vertex at the center of the circle. So here I am at the center of the circle, O, and I have an angle with its vertex at the center. Angles are labeled very specially. We want to pay attention to this. If this was point A and this was point B over here, we would call this angle AOB. The key is that the vertex of that angle is in the center of its description. Okay, so the angle AOB. A second type of angle that you're going to see is called the inscribed angle, and I would find this one's a little bit trickier, maybe because of the word inscribed. If you inscribe something, you're drawing it within the boundaries. For example, I could inscribe a square into this circle, okay, or a rectangle, I guess, into this circle. I'm drawing it within the boundaries of that circle. That's inscribed. So the inscribed angle is an angle that has all three of its edges, or sorry, endpoints touching the circle. So we start here, 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 and here is my vertex. So this angle here, we'll say A, B, C. Okay, so that's how we're going to write A, B, C like so. Okay, angle ABC is an inscribed angle. Something that's not on this page, and I think it might come up a little bit later, is the word arc. Arcs are important parts of circles. Arcs are the outer edges of the circle, part of the circumference. And we talk about arcs again in terms of the endpoints of these angles. So we start here with point A and point C. I have an arc, a great arc like so, with a little line above it, arc AC. Okay, so that arc's in between that angle ABC. So again, I just want to point out that this is the vertex, B, the vertex, and then A and C, that is where your arc is being formed. Okay, now that arc AC as I draw it, that's a minor arc. The reason it's called a minor arc is because it's small. It's the smaller arc. Where's the larger arc? Well, use my green marker here. If I start at A and I get to C, and I go the other way, so I still have arc A, B, C. You'll notice that I add the B in there because I need to tell the person who's interpreting this question that I'm going that direction. Anyways, arc ABC, we call that a major arc. Okay, so ABC, that's a major arc. That's just because it's bigger than arc AC. All right, and tangent on this page. Tangent might be a new word for you. It's not just tangent. We should add tangent line. So a tangent line, it's going to touch the circle in one location or one spot only. Okay, so right here where this line touches that circle, we call that the point of tangency. Okay, that's the point of tangency. What you should see is that this line here, okay, this line here, all right, touches this circle just in this one spot here. That's my point of tangency. And we're going to learn a bunch of different theorems that go with tangent lines and circles, but we just need to understand what a tangent line looks like. Not listed on this page for some reason is another kind of line. Might look something like this. Noticing that it touches the circle in two spots, so it's going right through the circle and has 2 points on the edge of the circle. That's actually called a secant line. Okay? Just take 10 seconds. Make sure you've got the information copied down that you need. Okay? I'll also have these saved. If you've missed something, you can come and see me in class tomorrow, and I'll have copies of the notes ready for you. Just to look at, you can copy them into your own notes. Okay, so if you've missed something, you can come and see me for that. Okay? Alright, you go to the next pages. We're going to see some definitions. So, kind of a repeat of what I just said. A circle, all points equidistant from one central point. There's circumference. I knew I would have included it. The distance around the circle. And remember, we had those two formulas for circumference. Circumference equals pi times d. Circumference equals 2 pi r. Radius, distance from the center of the circle to the edge of the circle. Diameter, distance from the edge of the circle to another edge, passing through the center. That's the key to the diameter. We know that the diameter has to pass through the center. And it's also relevant to know that 2 times the radius, okay, that equals the diameter. Many times we use formulas like the formula for the area of a circle, pi r squared, for example. But we'll give you a circle, and we'll give you a diameter, and we'll say that, that diameter is 10 centimeters. Find the area. And remember, your job then is going to be to know that the radius is then 5 centimeters. And you go area equals pi times 5 squared. Area equals 25 times pi centimeters squared. We can leave the answer just like that, or we can grab our calculators. Be somewhere over 70, at least 75 centimeters squared. 25 times 3.14. Okay, next slide. A few more definitions. Alright, a little bit of review of triangles. Might seem weird because we're working on circles, but triangles play an important role in the circles. So, a right triangle has one 90-degree angle. So, we'll see right triangles with that little square in the corner that's indicating that 90-degree angle. We do not make assumptions. Okay, we do not assume a right angle unless it's been marked a right angle. We can prove a right angle, and we're going to try that coming up with the theorems we're going to learn. But if you see a question and there isn't a right angle marked, we do not assume the triangle is 90. Scalene triangles. All angles are less than 90 degrees. That's acute. Okay, acute means less than 90 degrees. An obtuse triangle has one angle larger than 90 degrees. So obtuse means greater than 90 degrees. I always think those two words just sound exactly what they mean. Acute sounds really small and teeny tiny, so less than 90. And obtuse sounds large and overbearing, so greater than 90. Isosceles triangle. Two sides are equal and two base angles are equal. This is an important one for us. I want you to remember isosceles triangle. We're going to see quite a few isosceles triangles in that two sides are the same length. The two base angles are also equal to each other. If I could demonstrate an idea for this for circles, I'll just go down here. The reason this plays for circles is remember that the radii in a circle are the same length. So if I have a radius of 3 here, and I have another radius here, I know that that has to be 3 because the radii are equal to each other. If I were to join to create a triangle, I want you to be able to identify that you just created an isosceles triangle. Okay, so it's important to know that those radii there are equal, and that two sides of a triangle, when they're equal, are called an isosceles triangle, and then the base angles are going to be equal as well. Another important triangle is the equilateral triangle. So, the thing about an equilateral triangle is that all three angles inside an equilateral triangle are 60 degrees. all three angles are equal, all three sides are the same, that's an equilateral triangle. That leads me to the next point down here. It says if the sum of interior angles of a triangle is 180 degrees, what is the measure of one angle in an equilateral triangle? Well, I just told you that. So I think the most important thing on this is this statement right here. The sum of the interior angles of a triangle are always 180 degrees. Okay, so in every triangle, all three angles are going to add to 180 degrees. That's relevant information because if I give you any triangle and I say that this is 50 and this is 30, what is this angle going to be? You should be able to solve this by process of elimination. So far I've used 30 plus 50, I've used 80 degrees, so 180 minus 80 would leave me with 100 degrees for my missing angle. Okay, so that all angles adding to 180 degrees, that's an important piece of information for this. Alright, so more definitions. These definitions you probably heard and saw maybe grade 7 or 8. Hopefully, if you haven't, maybe they're new to you, but we'll get through them. Supplementary angles. Supplementary angles are two angles that add to 180 degrees. Okay, so the best example of this is maybe a square. So if I have a square, I know that all the corners are 90 degrees in a square, but I can say that this angle here and this angle here are supplementary to each other because they add to 180 degrees. Now, they don't have to be 90-degree angles to be supplementary. For example, 30 degrees is supplementary to 150 degrees because together that would add up to 180 degrees. Okay? What is the angle measure of a straight line? Think about that for a second. I'm going to show you a picture. Here's a somewhat straight line, and here's the angle we're measuring. Okay, any ideas? If we're not sure, let's think about a circle for a second. Oh, that's not what I want to draw. If we draw a circle, do we remember how many degrees are in one revolution of a circle? I think, I hope you're all yelling 360 degrees. Okay, so one revolution of a circle is 360 degrees. So that means the measure angle of a straight line you can see is a semicircle, right? We made a semicircle here. So half of a full circle, we would then say that's 180 degrees. So the angles that measure on a straight line, that's 180 degrees. Why is that relevant? Well, if I draw a straight line and I tell you that this is 70 degrees and ask you what this is, again, you should be able to do some subtraction, knowing that the full across here is 180. 180 take away 70, we end up with 110 degrees. Perpendicular, hopefully you got from the first page, two lines are perpendicular if at their intersection they form a 90-degree angle. That's the symbol for perpendicular. Okay, if you see that symbol, we know things are perpendicular. But again, we never make an assumption in a diagram that things are perpendicular unless you see the notation of the right angle. Okay, has to be a right angle for them to be perpendicular. Two lines are parallel. Okay, parallel and perpendicular sound a lot alike. I remember that this parallel is what it is because of the letter L's. Two L's in parallel, they're parallel to each other. That's what parallel lines are. They never intersect. So two lines that look something like that. Okay? Oh, a good one. Pythagorean theorem. I know you covered this. Okay, I know you covered this early. Oh, sorry guys. C squared equals A squared plus B squared. Couple of things we need to discuss about old Pythagorean theorem here. First of all, Pythagoras, the guy that the Pythagorean theorem was named after, he came up with this after measuring multiple triangles and finding this relationship between triangles with right angles. So that's key number one. Has to be a right angle triangle. He noticed this relationship between right angle triangles and their side lengths. The longest side of a right angle triangle is called the hypotenuse. It's a funny name. Okay, hypotenuse. And what he noticed was that the hypotenuse, which he's called C, has a relationship where this side squared is equal to this side squared plus this side squared. I just realized you can't see me do that. To A and B squared. All right, let's try this. So if we have a hypotenuse of 5, okay, and we have a side length of 3 and a side length of 4, we see 5 squared equals 3 squared plus 4 squared. So we have 25. Does that equal 9 plus 16? It sure does, right? We have 25 equals 25. That's Pythagorean theorem. Normally we're given two sides and have to find the third side. So if you want to just add this question, all right, let's say we're given 8 and 4. Oops, it's a 4. And we want to find x. So I purposely didn't call it C because it's not always going to be called C. You need to know that that's the longest side of the triangle. And the coolest thing I've seen so far to tell you about this is how Pythagorean shoots an arrow through his 90-degree angle, and that side that it goes through, that's the hypotenuse, that's the longest side. So it's always the one that's opposite that 90-degree angle. So we're going to set this up. X squared equals 8 squared plus 4 squared. X squared equals 64 plus 16. X squared equals 64 plus 16. How embarrassing if I got that wrong, okay? Let's say 80. And we don't leave it as x squared, we have to square root our final answer. And I don't have a calculator sitting beside me, and this is a really good introduction to, we don't have to get a calculator out. We can just leave it as a radical, that's what that's called, the square root sign. Leave it as the square root of 80. Okay. All right, that brings us to the interior angles of a triangle. So what is the sum of 3 interior angles of a triangle? We already talked about that. 180 degrees. If I know 2 angles in a triangle, how can I find the third? Well, I would add angle 1 plus angle 2, and then I would subtract from 180. If we wanted to write that out, we might just do something like this: 180 minus angle 1 minus angle 2. What is the measure of one angle in an equilateral triangle? Again, we know that in all triangles add up to 180 degrees, and all 3 angles are equal. So one angle is 60 degrees. Oh, good one. How can I determine the missing angles of an isosceles triangle if I'm given one angle? Well, there's 2 situations here that we have to look at. So let's look at the first one. So here's an isosceles triangle, and I know that this is 40 degrees. Okay? How can I find the measure of that angle? Okay? Well, if I know that this angle is 40 degrees, and this is an isosceles triangle, then I can figure out that that angle also has to be 40 degrees. Okay, so now that I know that that bottom angle is 40 degrees, I'm really just left with my top angle. And we know that I'm going to do 180 minus 40 minus 40, or 180 minus 80, whichever you want, to end up with 100 degrees. That's one. This is the harder one. This is the thing. This angle up here is 50 degrees. This is an isosceles triangle. We know then that those 2 angles are the same, but what are they? Alright, so I have to actually do my subtraction first here. I know that I've already used 50 degrees of my 180 degrees. So I'm going to subtract 180 minus 50, and end up with 130 degrees. Now again, remember what I just said. This angle and this angle have to be the same. So they share 130 degrees between the 2 of them. So what I need to do is take 130 and divide it by 2, and I would determine that both of those angles are 65 degrees. Okay? So when you come to class tomorrow, You're going to come in and work on some mental math, some problem solving. It'll be a review class. You're going to see some Pythagoras theorem, some angle solving, and just some other basic geometry review. So we'll see you guys tomorrow.